So this topic is 3.1, Intermolecular Forces, and the objective for this topic is to explain the relationship between chemical structures and molecules and the relative strength of their intermolecular forces when A, the molecules are of the same species, and B, the molecules are of two different chemical species. So we're going to go through our definitions and our examples of intermolecular forces. So reminder about polarity. So we have polarity influences the bonds in a molecule or a particle in three different ways. So we have three different categories based on polarity. So we have a non-polar covalent bond. So that means the electrons are shared perfectly evenly between the two atoms. This means that there is essentially no difference in electronegativity. If a bond is considered polar, it means that one atom is attracting the electrons more than the other. So this means that there is a larger difference in polarity or in electronegativity, but not enough to make it ionic. In a polar bond, we end up with a partial negative and a partial positive side of the bond. So the side that attracts the electrons more is going to be partially negative because the electron density is shifting towards that side. The side that doesn't pull on the electrons as much has a slight or a partial positive charge. We show partial positive and negative charges as having, it looks kind of like an S with the tail looped in. It's a lowercase delta with the superscript of the minus or the plus. We can have both polar molecules and polar bonds. So we're going to talk about polar molecules in a later topic. And then we can have ionic. So ionic is when there is a large enough electronegativity difference that the electrons are pulled from one atom to another. We make complete positive charges, complete negative charges, and then the fact that positives and negatives are attracted to each other is what holds those two together in the bond. So intermolecular forces are also called van der Waals forces. So these are attractive and repulsive forces. And there's three main categories. So there's dipole-dipole, dipole-induced dipole, and ion-dipole. So I'm going to go back just for a second. A dipole happens when there is a partial positive or a partial negative. So a dipole is going to exist when the electron density is shifted one direction or the other. So it's always going to exist in a polar covalent bond, and we're also going to talk about how we can have temporary or induced dipoles in non-polar bonds as well. So an ion-dipole, all of these strengths we're kind of going to keep Coulomb's law in the back of our mind. So we're thinking about size and we're thinking about charge. So size affects the distance. And then the magnitude of the charge is also going to impact it. So when we're looking at intermolecular forces, we're looking at the distance between the ion and the dipole. We're looking at the size of the ion charge, and we're looking at how much of a dipole there is. So how polar is that bond? So this is all coming down to electronegativity. This accounts for how ionic solids dissolve in water or are hydrated. So you can see from the diagram, we're using sodium chloride or table salt as our example. And so when table salt dissolves in water, it splits apart into its two ions. And the partial positive sides of the water molecule or the hydrogen. So oxygen has a higher electronegativity than hydrogen. So the electrons are going to be pulled towards the oxygen and away from the hydrogen. So that leaves the hydrogen with a partial positive and the oxygen with a partial negative. Well, the partial positive sides are going to be attracted to the negative ion, which is chlorine. And the partial positive sides are going to be the partial negative sides are going to be attracted to the positive ion, which is sodium. So when we draw our structures, our particle diagrams, we're going to show that the positive part of water, which are the hydrogens, are attracted to the chlorine, and the negative part of water, which is the oxygen, is going to be attracted to the sodium. If you look at the diagram, you might notice that there's a 2 delta minus next to the oxygen. So that's showing that it's pulling electrons from 2 hydrogens, not just from 1. So that's impacting how attracted those are. And so you can see the orientation looks a little bit different depending on the positives and the negatives. But what we're looking at here is an ion-dipole intermolecular force is always going to happen between an ionic compound and a polar molecule, so something that has a polar bond in it, because dipoles always exist in polar bonds. So that's an ion-dipole intermolecular force. So dipole-dipole is when you have two polar molecules, so water, for example, and so they're going to have partial positives and partial negatives, and then opposites attract. So the partial positive of one molecule is attracted to the partial negative of another molecule. This affects vaporization and condensation of liquids, so going back and forth between liquid and gas. So this is often looked at in terms of vapor pressure. So if you have a stronger attraction, you need more energy to release or break those attractions. And so you're going to have a lower vapor pressure because there's going to be less molecules hitting the surface of the liquid. This also affects, we look at this one often when we're looking at boiling and boiling point, because in order for something to break those attractions and go from a liquid to a gas, you're going to need more energy if you have stronger attractions. So things that have stronger intermolecular forces have higher boiling points. Things that have weaker intermolecular forces are going to have lower boiling points because it's going to take less energy to break those attractions and make that change happen. This also looks at or considers solubility. So the phrase we like to use is like dissolves like. So things that have similar intermolecular forces are going to dissolve together. If they have different intermolecular forces, they're not going to dissolve. So we want, in order for things to be able to dissolve and mix evenly, you need similar intermolecular forces. And so the phrase there is like dissolves like. And then there's the diagram here that shows how the attraction between the two molecules works out. It's the same. Positives and negatives are attracted to each other. Just in this case, they're not ions. They're the partial positives and the partial negatives of polar bonds in molecules. Hydrogen bonds are a form of a dipole-dipole. They're a very specific kind, and they are the attractions between, so it's due to the fact that hydrogen-oxygen, hydrogen-nitrogen, and hydrogen-fluorine bonds are extremely polar. And so that means they have really strong electrostatic forces. So those partial positives and partial negatives are really strong compared to other polar bonds. And so because of this, they form not just your simple dipole-dipole, they form one level stronger, which we call hydrogen bonds. It's a little bit of a misnomer because they're not actually bonds, they're an intermolecular attraction. So they're not sharing or exchanging or transferring electrons like they would in a covalent or an ionic bond. However, they are extremely strong intermolecular forces. So these attractions are going to happen between a hydrogen in either an HO-HN-HF bond and an oxygen, nitrogen, or fluorine. So there's a couple of examples here. So there are several instances where hydrogen bonding is super important. One of those is in DNA. The other one is in the unique properties of water. So the fact that water forms hydrogen bonds explains why ice or solid water is less dense than liquid water, because once they lock into those arrangements, they actually spread out farther than when they're in the liquid form. And they have more fluid attractions. This also relates to the high heat capacity of water, because since they're forming all of these really strong attractions between the molecules, it takes a lot of energy to be able to break those, which means the material itself has a high heat capacity. And then the next one is dipole-induced dipole. So dipole-induced dipole happens when a polar molecule is next to a non-polar molecule. And what happens is it very briefly causes a dipole. So if we use water as our example, if a water molecule, which always has a dipole, it always has polar bonds. When it goes next to a non-polar molecule, it very briefly and just temporarily pulls the electrons from one side to the other, or actually you can think of it as it pushes it away. So the negative side of oxygen, which has the higher electron density, is actually going to push the electrons away to the other side of your nonpolar molecule and create a very brief, very temporary partial positive charge. So it only exists while it's next to that polar molecule. We talk about this in terms of polarization or polarizability. Things that are more polarizable or have a higher polarization are things that have a high molar mass. And that's because if you have a high molar mass, you're going to have more electrons, which means a larger electron cloud, which means that it's easier to make it polarized. So things that are big are more likely to be polarized temporarily than things that are small. So bigger things are more likely to have induced dipoles than smaller things. And then our last one is induced dipole and induced dipole. So this is when, this occurs between all molecules. We sometimes refer to these as London dispersion forces or LDFs. These actually, although they're the weakest, account for most of our intermolecular forces. And again, this goes back to polarizability. And so you can imagine instead of having a polar molecule next to a nonpolar, and the dipole inducing a dipole on a nonpolar molecule, they're just constantly inducing dipoles on each other because you have to remember that these are molecules, these are particles that are always moving, the electrons are always moving, and so there's always a possibility for a brief induced dipole, which is going to create a temporary attraction. So again, this occurs between all molecules, so everything has LDFs or induced dipole. And again, the stronger LDFs, if you're comparing them, if that's all they have are LDF, the bigger molecule is going to be more polarizable, and therefore it's going to be stronger. Because again, if you have more electrons, they can be moved more, which means the more you can move the electrons, the greater partial negative, partial positive you can have, which means the greater attraction you can have. So big things, more polarizable, therefore they can have stronger attractions. But these do exist in all of our molecules. And then the last one that I wanted to point out, this isn't its own intermolecular force, but it's just the idea that intermolecular forces can exist between separate molecules, which is what we talk about the majority of the time, but it can also exist between different regions in a molecule. So we see this a lot in DNA, where different regions of the molecule will be attracted to each other. We also see this a lot in proteins, where they're big and they'll fold in on each other. And so the regions will form intermolecular attractions between other regions. And those attractions have a lot to do with the structures and then therefore the function of those molecules. So intermolecular forces are a really key part to how our large biomolecules actually work and accomplish what they need to accomplish. So one of the things you'll be asked to do most often is look at the strength of these intermolecular forces. And so our weakest intermolecular forces are London dispersion, or induced dipole, or LDFs, whatever you want to call it. When you're comparing London dispersion, again, bigger is stronger because bigger means more polarizable. The next up is the dipole-induced dipole, again, because it only exists when the dipole is next to the induced dipole. Up from there is our dipole-dipole, so when you have two polar molecules next to each other. The version of dipole-dipole that's stronger is a hydrogen bond, so that exists in those specific situations when you have a hydrogen that's in an HO, HN, or HF bond attracted to an O, an N, or an F. So there's specific scenarios in which hydrogen bonds occur, but they are very strong, and that is due to the very large electronegativity difference between hydrogen and those three other elements. And then the strongest is our ion-dipole, and that's because the ion always has a charge. It's not induced or based on anything else. It is a full charge attracted to a dipole. So those are your intermolecular forces, the rundown of what they all mean. The most often questions you're going to be asked are to identify all the intermolecular forces that exist between certain molecules, to discuss their strength, and to relate their strength to their properties. So you'll want to keep in mind that the stronger the intermolecular force, the higher the boiling point, the greater the melting point, the more energy it's going to take to do anything. So that's going to affect its vapor pressure. That's going to affect again, the boiling point and the melting point. It's going to affect its solubility depending on what intermolecular forces it has. So those are the types of things that you're going to have to look at. Identifying the forces, discussing why certain ones are stronger than others, and then connecting the forces to the properties. So that's what our practice is going to primarily look at.